we're live.
And we're live. Welcome, everyone.
Welcome, everyone, to Astronomy on Tap number 35. I am your MC, Blue Moon Skater Girl, and
I am MC Carbon Queen, MC Blue Moon Skater Girl. What is your beverage of choice tonight?
My beverage of choice is this Malbec wine
That's
from
very fancy.
2020 or something. What about you? What are you drinking?
I am drinking some very fancy instant coffee.
Oh, wow.
I'm gonna have a long night. I'm running a telescope observing run the next 2 nights. So I'm trying to
awesome.
my schedule. Yeah, I'm very excited. It'll be fun.
I guess people should know astronomers tend to flip their schedules on a regular sometimes, especially when observing.
Yep. It's suddenly night is day and day is night. It's very confusing.
All right, so as a reminder, this is Astronomy on Tap, and we are astronomers at Texas A&M, grad students that put this together every month to teach people about the universe. So welcome again. And to start, we have a quick statement that we wanted to share with everyone. So
to begin our night, we wanted to address some important recent events. As we've shared on the show before, a common misconception among scientists and the general public alike is that science is apolitical because the scientific method is meant to be an objective process. Therefore, it's common for people to criticize scientists, especially those from historically marginalized groups, for speaking out on political or societal issues. However, attempting to silence scientists for speaking out against racial injustice in science and society at large is itself a political act. These attempts work to maintain a status quo wherein historically marginalized groups at best are constantly marginalized and inconvenienced, and at worst are murdered. Science is absolutely political. It's conducted by humans who are intrinsically political, and according to the wills and morals of their society, which are political. So as scientists performing outreach with Astronomy on Tap, we have a public platform, and it's our duty to speak out on issues of justice, especially when those affect our own institutions. So yesterday we heard the verdict from the trial of the police officer who murdered George Floyd, where this officer was found guilty on all 3 counts. While this is a moment to celebrate, this is not justice. This is accountability. True justice here is impossible because it would require George Floyd to still be alive and still with his family. The closest to justice we can achieve is to prevent the murders of more Black lives and repeated generational trauma that those murders cause these communities. We're grateful for the outcome of this trial, but acknowledge that so much work is left to be done, and we cannot allow ourselves to become complacent. So thank you.
Thank you so much for sharing that. Okay.
All right.
So moving on to our announcements. Okay, so we are still doing trivia, and you can access the trivia by going to text.ag/AoT trivia. And if you participate and you get the most answers right, you can win a prize and you will be emailed.
The great sound. Like and subscribe to our YouTube channel. We always love that. And then if you like and subscribe, then you can stay attuned to everything that we're doing and all the fun stuff that we put out.
Follow us on our social media pages. That is Twitter, AoT_BCS, and on Facebook and Instagram, you can find us at AoT BCS. And then you can also go to the main page, astronomyontap.org/events, and you will find us there, as well as other Astronomy on Taps happening around the world and in the nation.
Also, in the before times when we could do this in person, we had so much fun doing this event at the Grand Stafford Theater, which is a historical theater in downtown Bryan. Unfortunately, because of COVID, we haven't been able to do this in person for over a year now. So if you would like to help tip our bartenders that would be bartending for this event and help support them during this time, feel free to Venmo the owner of the Grand Stafford, Jose Quintana, at Jose Quintana 20, and just put Stafford Tip in the description and it'll go to the right place.
And you can also Venmo us or cash up us at AoT BCS. And if you give us $15, you will get a t-shirt. So
Yay.
Please support us, the grad students that are making this happen.
And our next event will be May 19th, 2021. And if that's hard to remember, it's the third Wednesday. So.
Okay, and lastly, put your questions in the live chat and we will ask our speakers directly. So don't wait and forget, you can just put them on there. Okay.
Excellent. All right, so our first, oh no, you're introducing our first speaker.
No, our first speaker is Vince.
Oh, okay, never mind. Our first speaker, we're just excited. We want both of them to go at once. Our first speaker is Vince Estrada-Carpenter, who is a soon-to-be a PhD from our program. Some fun facts about Vince. Vince hasn't had a haircut since January 2020. He already had long hair before that too, so this is very exciting. He has a 4-month-old, and his favorite midnight snack is basil, just fresh cut basil. Additionally, some exciting news. Vince, after he gets his PhD, will be heading out to St. Mary's University in Halifax, Nova Scotia, Canada, to join the James Webb Space Telescope, NIRISS, which is an instrument on the James Webb Space Telescope, join their GTO team and get like some of the first access to this new space telescope data. So it's very exciting. Vince, if you'd like to join us. Welcome, Vince.
Hello.
What is your beverage of choice for the night?
Water.
Oh, that's good. That's fair. All right, well, take it away.
Take it away, Vince.
Yeah, thanks you all for coming. Excited to give this talk. I'm not sure. I think this is my 4th Astronomy on Tap talk. And every single one I've done, they've never actually been over the research that I do at A&M. So I decided, why not actually talk about my research? Well, I'm not going to talk directly about my research, rather the stuff that I study, some of my results that have, gone into that work. So I'm going to talk about the formation of massive galaxies in the early universe. And really what I want to know is, what can we learn from these massive galaxies in the early universe? And so I'm going to leave you with the Hubble Deep Field, is just like that image, while I give you a bit of background on why this is an interesting topic. So when I'm talking about massive galaxies, I'm talking about massive, yes, they formed an incredible amount of stars. In fact, the type of galaxies that I'm talking about today, they formed hundreds of billions of solar masses worth of stars in less than a billion years. That's a long time. Billion years is a long time, but that's also a lot of stars that formed. These are mature galaxies. They're basically done. Some people refer to these galaxies as red and dead. Quiescent galaxies, another term for it. I'll probably call them quiescent galaxies a lot. They basically done everything. They formed all their mass, and now they're just going to sort of sit there and sort of just evolve passively throughout time. But to have formed all that mass in such a short amount of time is incredible. And one of the big things is we really don't know how they form. I mean, we have a sort of an understanding, right? We're not totally ignorant on the subject, but there's a lot that we're lacking. In fact, when we take our models of galaxy evolution and push them through simulations and try and then when we look at the numbers, we find that we fall a lot short from what we've seen in the universe. In fact, a number I've seen pretty recently was around 30%. So our simulations can't produce the amount of massive galaxies that we're seeing. So there's something lacking in our understanding of galaxy evolution. And so a bit more background on these. And so we can take galaxies and we can stick them into 2 groups, generally. We have star-forming galaxies. These are gas-rich, they're blue in color, and they're forming stars, right? The type of galaxies that I'm more interested in are the quiescent galaxies, again, red and dead. They're gas poor, and they have extremely low star formation. Not that they're not forming any stars, it's just such a low amount. And in fact, this right here, this is a quiescent galaxy. This is a massive elliptical galaxy, but this isn't the type of galaxy that I would study. This is. And in case you didn't see what I just did there, the thing that I'm pointing at, that's actually the type of galaxy I would be studying. And it's massive, right? It looks tiny because it's very far away. And again, so these galaxies that I'm interested in are in the early universe. And without going too deep into where redshift is, these are galaxies at higher redshift, not the highest redshift. There are people here who study much higher redshift galaxies, but these are pretty high redshift galaxies to have, again, fully done evolving. And the higher the redshift, the further back in time we're looking. And so this is how we study galaxies in the early universe. So one of the things that we've learned from these galaxies is about their morphological evolution. And this can, tell us about all sorts of things. This is one of the things I'm most interested in. So this plot right here, this is actually the plot from my advisor, one of his papers. And what you're seeing here is different galaxies at different points of the age of the universe, right? And all you really need to know is that at the top, we have sort of the more recent galaxies, although these are still, pretty young in the universe's age. But as we go down towards the bottom right, we're going more and more into the younger part of the universe. And but the mass here, and this is the important part, the mass, the amount of stars is basically the same for all these galaxies. What you're seeing is they're getting smaller and smaller, where they're getting more compact. All that stellar mass is being shoved into a much smaller area. And basically, as we look further back in time, these massive quiescent galaxies are getting more and more and more compact. In fact, the kind of stuff that I study are more like these. They're just these little spheroidal galaxies. They don't really have much of a shape. They're just little blobs. Now, there's a lot of, people have a lot of opinions about how do you form these compact quiescent galaxies at high redshift. And we just tell you my ideas on this because I've done research into this. So for my 2020 work, I found this relationship, which basically says that when a galaxy formed is correlated to how compact it is, such that the galaxies that formed the earliest are all compact. Galaxies that formed later, some of those can be compact, but they are also more extended in their profiles. And to just give a very sort of, brief blanket explanation of how this sort of works. Well, we know that the universe is expanding, right? So if we go back in time, the universe was smaller and everything was more dense. And you see the material that forms the stars that make up these galaxies, it can't do it on its own. It needs something else to allow it to collect. It needs these dark matter halos. And back in time, these dark matter halos were also more dense. They're smaller. You can think of them as sort of buckets to collect all the stuff that we need to form stars. And in the early universe, the buckets are a lot smaller. So the galaxies that form are also going to be a lot smaller. But as the galaxy ages, the buckets get bigger. The galaxies can also get bigger and more extended, forming the same amount of mass, but the profiles are a lot more extended. And so just studying the change in how compact these galaxies are can tell us a lot about the evolution of these dark matter halos. Something else we can learn from these massive galaxies is about chemical evolution within these massive galaxies. Now, here I have a periodic table. I really like this periodic table because it tells you where all the elements come from. We have stuff from the Big Bang, emerging neutron stars, and you can see where they are here. This is really cool. But for most astronomers, the periodic table actually looks like this. We have hydrogen, we have helium, we have metals. And one of the measurements that we can make is something called metallicity. It's basically what's the chemical enrichment? How many or how much metals are there in the galaxy? And these metals, again, I just showed you where they come from, right? They're mostly coming from stars. And they're generated through successive formation of stars. Stars, right? You get these massive stars, they form lots of metals through fusion, they die, they release all that stuff, which can then turn into another set of stars, and the cycle goes on. And through each successive cycles, we enrich the galaxy more and more. The stars get enriched. And there's two types of metallicity that we study in my field. It's a stellar metallicity, that's the metallicity of the stars, and gas phase metallicity, the metallicity of the gas. And some work I did in 2019 was about the metallicity of the stars, right? So how enriched are the stars? And there's a relationship that's well known in my field called the mass metallicity relationship. Basically, the larger the galaxy, the more chemically enriched it is, right? So the more massive the galaxies are, the more successive cycles of star formation they've gone through. And what's interesting about this relationship, and something that I saw in my work, is that it appears that no matter how early we've looked, as far as I've looked, because I have one of the highest redshift studies, this relationship doesn't change, right? The most massive galaxies tend to have stars with about the chemical enrichment of our sun. And we would call that a solar metallicity. And so if we look at these types of galaxies in the current universe, right, and in the nearby universe, we see this relationship. We look a little bit further, we see the same relationship. We look as far as I've looked, the exact same relationship. It doesn't change, it doesn't evolve with redshift. And that's really interesting because that possibly means that the process of getting up, of enriching stars up to this point is somehow linked to them quenching, whether it's involved in the mechanism or it's just some other factor. We don't really know why this is the case. And this can change, right? With James Webb coming, we're going to be able to go and look even earlier in time. And it's possible that at the very earliest times, the very earliest quiescent galaxies have different metallicities and has a different relationship. We don't know, and that's something exciting coming from James Webb. One of the other reasons that this is interesting and that it doesn't evolve is that the other relationship that I talked about, the gas phase metallicity within the gas does change with time. So if you look at galaxies now, look at their gas phase metallicities, you see one relationship. And as you go further and further back in time, you see that that relationship changes. And so this is really strange that one of the metallicity relationships changes, the other one doesn't. Now it's possible that, again, the stellar metallicity one will change eventually. We don't know. And this one, the gas phase metallicity, is actually a lot easier to measure than the one that I do. So we've been able to actually push this to a lot earlier in the universe. So it's completely possible that that can change, but we don't know yet. That's one of the exciting things coming from James Webb. Another thing we can learn from the chemical enrichment, the galaxy, or something we actually have learned, is about something called alpha enhancement. This sounds pretty complicated, and it is a bit complicated, but hopefully I can explain it. So what alpha enhancement means is that we have more alpha elements than we do iron. Alpha, and what's interesting about that is where these particles come from. So the alpha elements come from massive stars, while iron typically comes from type 1a supernova. And these two objects live on totally different timescales. Massive stars are on pretty short timescales. Right? They grow, they evolve, and then they die on pretty short timescales. It takes a lot longer to produce type 1a supernova. And so what alpha enhancement means is that the galaxy has been around and forming stars long enough to produce lots of these massive stars, have them die, and go through the cycles of forming successive stars, but not that long to form lots of type 1a supernova. So that means that the formation periods of alpha enhanced galaxies is really short. And what we see is that as we go further back in time, more and more galaxies are alpha enhanced. And so these earliest massive galaxies have had some very active star formation histories. They've been forming stars at really rapid paces. I mean, again, they're forming massive amounts of stars and they're forming them extremely quickly. And that's interesting. And that can tell us about another area of astronomy, and that's about reionization. And so here's a brief history of the universe, right? We have the Big Bang, and shortly after we sort of have this particle soup. It's very hot and it's ionized, which means that, electrons and protons are separate. But as the universe cools, it gets cool enough that the protons and the electrons start forming atoms. You start getting hydrogen and helium, and we create the neutral universe that we see right here. Now, if we fast forward to today, the universe is full of ionized gas, which means that those protons and electrons are separated. And you can separate the electrons from the protons by hitting them with hard enough radiation that it can actually separate. So somewhere in between, this process of reionization happened. And we know some about reionization, right? We know basically the period of the universe over which it happened, but one of the big mysteries is, what did the reionizing? There are definitely some candidates that are looked into. AGN, which I won't go into what an AGN is. My undergrad advisor would call them the most powerful engines in the universe. They produce massive amounts of radiation. So they're one of the candidates. Galaxies are another candidate. They can produce massive amounts of radiation, mostly going to come from the very massive OMB type stars. And so if you have these massive galaxies, which are producing, again, they are producing tons of stars, they're going to produce lots of OMB type stars. What sort of contribution do these galaxies have? And by studying the very massive galaxies in the early universe, we can sort of get an understanding of what their contribution to reionization would be. And so, yeah, thank you all for listening to my talk. I know I touched on a ton of different topics because there's a lot we can learn from these massive galaxies. And so if you have any questions, feel free to ask, and I'll try my best to answer. Thank you.
Thanks so much.
Thank you. Galaxies are incredibly interesting, in my opinion.
We're biased, but yes, I agree.
Yeah, true. It looks like we don't have any questions in the chat.
I have a question. So you did this great job of showing, the incredibly massive galaxies, like the big ellipticals and that tiny little fuzzy dot, which is the ones that you care about. Is there a particular age in the universe, or redshift, however you want to translate that, that's your favorite, and why?
My favorite redshift. I mean, redshift 1.6 is just very specific, but it's just.
Do you also say what that translates to time-wise?
Oh, I have no idea.
All right, we'll figure it out.
It's just because some of the data I have, which is a pretty unique type of data, we have some clusters that we've found at 1.6, and some really interesting results can come from that. So I'm really interested to see specifically these galaxies at 1.6. But I mean, in about hopefully, a year and a half, I'll be interested in redshift 2 and 3 more than that, hopefully.
That's true. Especially with all the cool data you're going to be getting from the James Webb Space Telescope, which is exciting.
Yeah.
Also, according to my calculator, that's the word. Redshift 1.6 is about, the universe was about 4.1 billion years old at the time.
That is so far. I mean, it doesn't seem far maybe to you more XGAL people, but when you're looking at redshift 0.5, hearing 4 billion years, yeah, that's far. Mm-hmm. But yeah, thanks so much, Vince.
Yeah.
Excellent talk. Thank you.
Oh. It looks like we have one question actually in the chat, if you want to come back. So Serious Stargazer was wondering how you measure the chemical enrichment of galaxies from gas, etc.
So we would look at something called an emission line. Basically, you can excite atoms with certain amounts of energy, and then they will release certain photons, right? And we can, when we look at the data, we find signatures of these elements we can take ratios, and that's how we would look at the chemical enrichment of these galaxies.
Nice.
We have another question. So Yazon asks, what is the timescale of the metal enrichment? It seems that there are a lot of metal-rich stars at somewhat early times.
Yeah, that I don't know. That would be really interesting to know. So when I'm studying these galaxies, I'm studying them when they're done, right? They're done evolving. And so I basically it's sort of, this is a bit grim, but it's sort of like an autopsy, right? I see what it's like at the end. There's other astronomers who do sort of study them while they're active, and they might have a better understanding of what those enrichment timescales are.
Great. Thank you. Okay. That's it.
Thanks again.
Thanks for coming back. Okay. So up next, we have a new segment, new-ish, started a couple months ago. It's called Who's Up, and it's by our very own Carbon Queen.
Yes.
And here we highlight different astronomers that you should follow on social media, or kind of like their important work that they're doing. And yeah, take it away.
All right. So welcome, everyone. Let me move the faces away. All right. Yeah, so this used to be a What's Up segment, but now Who's Up? It's a very clever way of what we think we're clever of trying to come up with this new name. Yeah, so Blue Moon Skater Girl did a great job describing what the segment's about, but just to kind of give you another summary and with words on the screen. This is going to be a semi-recurring segment. We've already had 3 installments. There's 2 installments of this, which is exciting. But we'll just be highlighting different active astronomers and the awesome science and other work that they do. And I'll be linking their social medias, primarily Twitter, but other things as well, like their websites and stuff. And so you can follow them on social media. So yeah, so to get us started for this month, I will only be talking about 2 people, but I first wanted to focus on Dr. Moya Mcteer, who is awesome. Her Twitter is GoAstroMo. You should absolutely go follow her. Go look at her website, follow all her social medias. She's an astrophysicist, a folklorist, a writer, and an amazing science communicator, all these things in one. She's written a book. She goes to lots of speaking engagements. One of my favorite things about her is she's incredibly good at storytelling. And so she's one of those scientists that really tries hard to tell her science and other people's science and the discoveries and the way we do science in a storytelling way. And so you're able to kind of get a really great big picture of what's going on, and also have a better appreciation for, where her particular science, for example, would fit in to the general story that is the, cosmic history of our universe and how it's created and how it's growing and evolving and all that fun stuff. So her website's really fun. You should definitely check it out. She has lots of information on there. But she also, just to give you some insight on the kind of science that she does, some of her research has included working with exoplanets, and she has really great graphics like that on her website. And then her most recent work has been focused on stars within our own Milky Way and the number of stars, for instance, in our galaxy that have encounters of some kind with other things in our galaxy. And it's a really great work, as you would probably expect, seeing as she's such a great storyteller and she's also a writer in her own right. She's really good at writing science papers, and so they're really easy to understand. You should definitely go check those out. So yeah, that's the kind of science that she does. But the other thing I really wanted to highlight is she has this podcast, because she can't just do tons of things. She has to do tons of things plus one, because she's very talented. So this is a really cool podcast called Exolore. And for all of you sci-fi nerds, this would be perfect for you, because just to pull a description from the Exolore podcast website, astrophysicist, folklorist Moya Mcteer explores fictional worlds by building them with a panel of expert guests, interviewing professional world builders, or reviewing the merits of worlds that have already been built. It's a really cool podcast. You should check it out. Yeah, I could go on about this, but I won't, to spare you all the time I could take up. But yeah, it's really cool. You should definitely check her out. And also, she's a newly minted PhD. She just did this really awesome defense, which I think is on YouTube, because it was a live stream to YouTube. And so you can go look that up and go watch her cool PhD defense as well. The other scientist I wanted to highlight this month is Rebecca Larson. So Rebecca Larson is an astrophysicist and NSF graduate fellow at UT Austin. She's also a US Air Force veteran, and she's one of the hosts of the Austin Astronomy on Tap, which is also excellent. You should go watch them when they have shows. Her Twitter is Saturn's Wings, her email, her website, just, Saturn's Wings. She's great. So what her science is the kind of science that I do. So I'm incredibly biased when I say it's the most interesting science. But what you're seeing here, for instance, an example, she looks at the most distant galaxies ever found. And part of her science is to try and find the most distant galaxies ever found. And so this requires her using, these 10-meter wide, essentially 30-foot wide telescopes in Hawaii, or using, these space telescopes, and having, primary access to the James Webb Space Telescope when it comes out. She's in parts of lots of collaborations that will get access to all this James Webb data, which is really exciting. So it's just an example of one of her work in 2018 of a particular distant galaxy that had never been identified before. And she identified it, which is super exciting. And so this is the kind of work that she does. She's super cool. And I've already mentioned it, but she's part of lots of James Webb Space Telescope things. This is just a GIF. I have no idea if it's going to be super laggy for you, but it's just kind of showing the James Webb Space Telescope unfolding in space, because we can't just shoot it up in space as is. We have to compress it into a rocket to get it into space, and then it unfolds in space while speeding out to its new home, which is the location Lagrange point 2. If you can look that up for the Earth, Sun, and Moon, and Lagrange point 2. So yeah, so she does a lot of really cool work. You should definitely go check it out. And check out her website, so she'll update it, because I keep making her. But yeah, so that's it. So that's all the people I'm going to highlight for this month, but stay tuned. We're going to have more scientist highlights. As many AoTs as I'm allowed to do this, it'll be very fun. And thank you so much. That's all I have for you.
That was awesome. Thank you. I'm definitely going to check out the Explore podcast, because I had not heard of it.
It's so cool. It's a really cool podcast. Yeah.
And it's great to highlight that astronomers are also very involved in science communication. It's part of what, or at least what we like to share with the world, is what we're doing in our field. So I think that's really important to get to a lot of different communities as well, which is why we do this.
Yeah, no, exactly. Yeah.
So thank you. And up next.
Next we have In the News with Dark Matter Dude. Where is Dark Matter Dude? Oh, hello. Dark Matter Dude, how are you doing? What's your beverage of choice tonight?
I am drinking a Kentucky Mule, which is, I've been told, a Moscow Mule, but with bourbon.
That sounds amazing. That's perfect.
Okay.
It's pretty good.
All right, we'll take it away.
Yeah, okay. I'm gonna try to share my screen here. Cool. And we are gonna talk about what happened in the news for this month of April. Once my buttons work. Okay, this should work now. Great. Okay, so first thing, hard to miss. Ingenuity took flight. Right. So this is a basically test helicopter, kind of like a proof of concept engineering thing that NASA put on the Perseverance rover, and sorry, the Kentucky Mule is getting to me. Yeah. So Ingenuity is a helicopter that basically just was an engineering feat. Can we run a helicopter on Mars for any appreciable period of time? So just a few days ago, they did their first controlled flight outside of Earth. You can watch the kind of YouTube video of this. So the helicopter's right there, and eventually it's going to rise up. It rose up about 3 meters off the ground, stayed there for about 30 seconds, and then came back down. And this is a camera that's on Perseverance is the viewpoint that you're seeing this from. So this is so cool. Basically, this is a very hard thing to do because the atmosphere is so thin on Mars that this is basically the equivalent of flying about 3 times the height of Mount Everest on Earth. No helicopter on Earth has gotten nearly as close to flying in those types of conditions. So this is just super awesome. There's more flights planned, including a flight where they're not just going to go up and down. They're actually going to go laterally, including going out to possibly even 300 meters away from the rover, which is super cool. And one thing that this is actually somewhat useful for is that there's currently a planned mission where they're going to send a quadcopter, so a helicopter, but with 4 spinning wings, out to Titan, which is a moon of Saturn, and that's a project called Dragonfly. So they're using the experience of this, and some of that will apply to the moon on Saturn as well. So that's really cool. And now the video is just gonna play again. Okay, great, cool. So this is not strictly astronomy, but we're still gonna talk about it. So yeah, so this is super cool. There's a super cool result from the particle physics community talking about muons. So muons are subatomic particles. They have a negative charge. They're a lot like electrons, except they're much more massive. They're about 200 times as massive as an electron. They have their own spin and their own magnetic moment. So when you put a muon in a magnetic field, it precesses that, kind of like a spinning top. So you get some angular momentum from a top spinning, and then it'll like precess around it if you kind of nudge it a little bit. Same concept, but with particles instead. So the parameter that describes this precession in a magnetic field is called the G factor. And this G factor is very, very close to 2, but it's not quite 2. And the deviation from 2 is because when this muon is in a magnetic field, it interacts with what's kind of called a quantum soup around it, where particles can just pop in and out of existence. And it's interacting with all the other particles that we know of in the standard model. And so what these people did was measure G, or G minus 2 is what they also call it. So this is the muon G minus 2 experiment, and they measured what this G factor is, and the value that they got was significantly deviated from the theory. Okay, now there's 3 explanations for this. One is that the measurement is wrong. That's still possible. This hasn't reached the type of threshold that particle physicists generally consider to be a new discovery of new physics. That's a 5 sigma threshold, if you've heard of that. This is around 4-ish sigma. So still pretty significant, but not the level that particle physicists usually consider. Route 2 is that the theory itself is wrong, and this actually might be the case. So this calculation is very complicated. It involves taking all the particles that we know of in the standard model of physics and doing very complicated calculations for how they would interact with this magnetic field in this muon. And it's easy to just get the theory wrong that way. It's worth noting that there's kind of a competing method of computing this theory using supercomputers. And when they calculate a value, their value is closer to the observed value than this original theory value. So that's 2, the theory might be wrong. Or 3, there's something new in the theory, some new physics, some new particle that is actually interacting and making G further away from 2 than we think it should be. And if that's true, that would be super cool. And it might even point to solutions to the dark. It could be like a dark matter particle. It could be something else that solves a whole bunch of astronomical problems that we've been having. Because if the standard model is wrong, then we kind of need to just revisit everything, So yeah, so that's super cool. Third story here: the stablest optical clock in the universe. And so we're talking about a white dwarf here. So the typically a white dwarf is the end state for about 90% of stars. And so this is just you've burned off most of the external layers, and you're not fusing hydrogen anymore. You're just sitting there, stewing, a little tiny star about the size of Earth. Now, if you look at the star, the star is pulsating a little bit. There's small changes in the amount of brightness that it gets. And so the period of this brightness is about 215 seconds. And it's a very small change. It's only like 1 part in 1,000, but you can still see it. And what these scientists have done is measured how the period of that pulsing changes over time. What they found, this is very impressive. What they measured is that if you use this as a clock, and you use this to keep your time, you would lose 1 second every 6.2 million years. which is an amazingly stable clock. You can use this kind of stuff to look for axions or planetary companions, because if there's a planet kind of perturbing the environment, that might be something that happens. So that's just super cool. I like to end on a cool image, and so this is the Large Magellanic Cloud, which is, if you're in the southern hemisphere, you can actually see, it's a satellite of the Milky Way. It's large enough that you can just see with your naked eye, staring up at a dark night sky. You can just see this with your eyes, no telescope needed. But this isn't just a picture of the LMC. This is a picture of the LMC taken from the moon. And so what this was, so this is work primarily led by a guy named George Carruthers. And so he did a lot of developments for far ultraviolet cameras and spectrographs. And so this is something he built and NASA put on the moon. So you can see this is the instrument that we're talking about. This is it on the moon. And this picture of the LMC is a far ultraviolet image taken from the moon. So that's super cool. And George Carruthers got the National Medal for Technology and Innovation back in 2011. And so this is him with a president, Barack Obama. So yeah, that's it. That's my news.
Thanks so much.
Thank you.
That picture just kind of blows my mind. This picture from the moon.
Yeah, it looks so big. Well, the LMC looks so big. But yeah, I mean, it makes sense. It's close. So
Relatively, yep.
Relatively close, right?
All right, thanks so much, Dark Matter Dude. So next.
We have our next speaker up next. All right, so I'm really excited about presenting this next speaker. Her name is Jenny Quinn, and she just graduated from Texas A&M University. She's one of my first friends at A&M, so she's leaving me to go to UC Merced for grad school in physics. So congratulations, Jenny. And a couple of fun facts. Jenny loves watermelon, and she plays the piano. And Jenny also just loves babies. She just loves babies. So welcome, Jenny. Hello.
Thank you for that introduction.
What are you drinking tonight?
Tonight I'm having an Australian whiskey.
Ooh.
Ooh.
Sounds delicious.
Yeah, it is. Okay,
Cool. All
I
right,
guess I'll
take it away.
just share my screen. All right, so today we'll be discussing, oh, sorry about that. Yep, today we'll be discussing the concepts of the multiverse, which is a really fun and interesting topic, although not something that I was really well aware with beforehand. But yeah, let's get started. So we'll be discussing the universe, first of all, because you have to talk about the universe before you can talk about the multiverse. We'll be discussing the multiverse afterwards, concepts and theories of the multiverse, and then talking about some conclusions that we can get from this. All right, so what is the universe? Well, I think we all know generally what the universe is. It's everything that we know: stars, galaxies, planets, buildings, planes, you and me. And it was created from the Big Bang a long time ago. And you can see some nice photos that I have here of galaxies, and here we are on Earth right here in the solar system. And so that's kind of what the universe is. And let's just talk a little bit about the history of the universe. So the idea was first proposed by ancient Greeks and Indians, and ancient Chinese philosophy included space and time in this, what the universe is. And so initially they had a geocentric viewpoint. And so a lot of historical mythologies and stories about the universe about the origins of the universe kind of had Earth at the center. We were created first, and then everything else was created around us, which I thought was somewhat amusing. And so now general relativity is the modern day theory used in looking at the origins of the universe. And so now we can move on to what a multiverse is. So the multiverse is a hypothetical, important thing right there, hypothetical group of universes that make everything in existence. So space, time, energy, information, matter, the physical laws that constrain physics and math, and the constants that describe them. And so we can talk now a little bit about parallel universes. And so we have kind of this science fiction version of the multiverse, as I'm sure we've seen in shows and movies, where, you know, every single different alternate universe is basically just, you know, it's you, but instead of taking a left today on your way to work, you took a right. And so that kind of creates an alternate parallel universe. And so that's actually one of the classifications of what the multiverse is, and we'll talk a little bit more about that later. But you know, that's the science fiction version of it. And so today we're going to talk a little bit more about kind of the physics and cosmology aspects of it. And so looking really quickly at the history of the multiverse, so ancient Greek philosophers contemplated infinite parallel worlds that arose from atom collisions a really long time ago. And so I think that's pretty cool that they were able to conceptualize that. And so we have Averroes, our dude on the right in the photo right here, entertained the idea of other worlds, although for his concept, they only existed in the mind of God. And we have Schrodinger's equation that paved the way for the hypothesis of the existence of a multiverse from the idea of superposition and having many states. And so we can see Averroes contemplating the multiverse in this photo. And so now we're going to go on to the concepts and theories, and we're going to look at 4 classifications, a few different types of multiverses, and black hole cosmology, which is a really cool concept. Right, and so we have level 1, which is the extension of our universe. And so our universe in this is basically what we can observe. And so we can observe everything within our Hubble volume, which is approximately 10 to the 31 light years cubed. So we can observe quite a bit actually. And so in this, there are infinitely many universes, which means that there exist universes very similar to ours in the way that matter is distributed. And so we can kind of compare this to the science fiction concept of parallel universes, where things are just slightly different in those universes. And so this is especially true in due part to something called the Cosmological Principle, which essentially means that if we were to look at the universe, or the multiverse in this case, really far away, if we were able to zoom out, everything would look exactly the same in terms of matter distribution. And so this kind of gives way to the idea that there are infinitely many universes that have similar or the same spatial matter distribution. So we have a lot of identical universes, and we just kind of have this depiction right here showing. We have our universe right here, and then right outside what we can observe in our observable universe, there's another universe and another universe over there. And so that's going to be level 1 of 4. So level 2 of 4 is universes with different physical constants. And so there are certain constants that describe the cosmology of our universe. They describe the curvature, the distance, the mass, energy content, and these constants are what models and describes our universe. And so we can kind of see that in the second image right here. And so the multiverse as a whole is stretching and will continue to do so forever. But essentially in this level 2 version of it, some parts and regions of space stop stretching and form distinct bubbles. And so you can kind of think of those as like air pockets. And so these bubbles that form are physically different from one another. And so that results in the same fundamental equations of physics, but different constants, particles, dimensionality, et cetera. And so maybe in one universe, right, you still have E equals mc squared, but C in that case may not be 3 times 10 to the 8th meters per second. That might be, 4 times 10 to the 8th or something like that. And so that's kind of the difference between multiverses and this level 2 classification. And so within this level 2 classification encapsulates level 1. And so each pocket that forms is a level 1 universe that I just discussed. And so moving on to level 3, which is the many worlds interpretation of quantum mechanics. And so this is kind of what we're most familiar with. It was coined by American physicist Hugh Everett III, and he introduced the universal wave function, the concept of universal wave function. And so that essentially says that Schrodinger's equation never collapses. And so every observable interaction that results from a given state or probability from Schrodinger's equation occurs simultaneously in branching parallel universes. And so this, we can see Schrodinger's cat unfortunately dies in one branching universe, but in the other is entirely fine. And so that's level 3 and kind of what we're most familiar with as well. And then level 4, this is the ultimate ensemble, and this is what's referred to as the theory of everything, or the mathematical universe hypothesis. And so all universes are equally real in this level and described by different mathematical structures. And so it can be used to describe any multiverse theory that we have currently, or that could potentially be thought of in the future. And so this, what I think is actually really interesting about this one is that it kind of looks at, it compares mathematics as a tool that we use versus a tool that we use that was brought and thought into existence by us humans and used as a tool to describe what we observe in nature and in the universe, comparing that to whether it's a pure fundamental structure that's inherent in the universe, independent of human interpretation. So would the laws of mathematics still kind of, I guess, exist and follow the same rules if we weren't here to come up with them, essentially? And so that's level 4 classification. And so now we go on to the different types of multiverses. And so I'm just going to talk about a few. And so we have something called the brane or cyclic type of multiverse. And essentially in this type of multiverse, the universe exists within a brane, which is essentially just kind of this right here, this plane over here. And it's just a physical object that conceptualizes the notion of dimensionality. And so these universes exist in the brane in a higher dimensional space, along with other universes. And so you have one universe on this plane right here, and you'll have like another one above that in different dimensions. And this multiverse comes across, so it's called cyclic as well, because when you have our brane, so the plane, the existence of our universe, if that collides with another universe due to any kind of force like gravity or any other forces that we may not even know of at this point, then that's when it's theorized that a Big Bang happens. And so the Big Bang erases all information from the previous universe and kind of writes over and starts over. And so that's the brane and cyclic type of multiverse. And you have the string theory landscape, which is a similar general idea to the classification of level 2, which is just different physical constants, but focuses on the fact that our universe is fine-tuned for life, and that the physical constants present in our universe may perhaps contain more meaning and significance than a simple random probability that our universe happened to have the constants that it does. And so, like, for example, the cosmological constant is one that's popularly talked about in this landscape theory, due in part to the fact that if it was just a little bit higher or a little bit lower, then there would not have been able to, then either the universe would be expanding too slowly for stars and galaxies to form, or it would have been expanding too quickly for stars and galaxies to form. And so there's no way that life could have came about. And so that's what this theory looks at. And then we have the classic type of multiverse, which is just simulations. I'm sure everyone's heard of this one. The idea that we could be living in a simulation and that we're all just, artificial intelligence. And so now we're going to look at something called black hole cosmology. And this is the idea that the observable universe is inside a black hole. So the universe that we live in right now is inside a black hole. And so basically, this means this gives way to the idea that we have a parent universe that we're in. So we are just inside a black hole, inside that parent universe. And it also gives way to the idea that every single supermassive black hole, the center of a galaxy, including the Milky Way, has a baby universe inside of it as well, which I think is a really interesting idea to think about. And so the Big Bang in this scenario could be explained as a result of the previous universe collapsing on itself, triggering a Big Bang, or by the formation of a supermassive black hole at the center of a galaxy, which is kind of what's shown right here. And so you have this black hole in this image, and you have a singularity, and that forms something called a white hole, which is the hypothetical antithesis of a black hole, in that nothing but light and information can enter the white hole, which is what our galaxy kind of would have come from. And you can see from this white hole, we have the regular progression of what our galaxy would be. And so that's black hole cosmology. And so now we can kind of look at, do we live in a multiverse? Well, I did talk to you about quite a few different theories of multiverses, and nothing actually very concrete. So you might have guessed that the answer is there's no way that we could possibly know. And so we have plenty to learn about in our own universe. And so fortunately, that's a fortunate thing. So there's endless discoveries to be made before we have to try and venture out into the realm of a possible multiverse. And so whether it's real or not, it's a really fun and interesting concept to kind of entertain yourself and learn about, even if it's not. I know a lot of scientists think it's more metaphysics than actual physics. And that's a debate that could be had, but I think it's still interesting and something that I had a lot of fun learning about when I was making this talk. And so, yeah, thanks so much for listening. Thanks for having me on Astronomy on Tap.
Thank you so much. It was such a fascinating talk.
Yeah, I definitely can't think about this too much because I will not sleep at night. I have a question, actually.
Yeah.
So do you believe that we live in a multiverse? So what are your thoughts?
I don't know whether I believe we live in a multiverse, but I guess I'd like to believe that maybe we do. I like the idea of that kind of mathematical looking at it from a mathematical perspective, like the theory of everything. I think that's really interesting, and it'd be really cool if it was true. Not that we'd ever know if it was, but so I guess my answer is I don't know.
Fair.
That's a good answer.
I don't think we have any questions in the chat at the moment.
Just blew us away.
Yeah.
Just processing. Well, all right. If we have any questions come in later, we can ask them.
Yeah.
Thanks so much, Jenny.
Yeah, thank you.
Absolutely.
This is great.
Okay. So up next we have trivia.
Oh yeah. Yeah, as a quick note, it was brought up in the chat. I forgot to mention this during my Who's Up segment, but Rebecca Larson is also an Arabic linguist. And for anyone familiar with the phrase 6 degrees of Kevin Bacon, she's kind of the astronomy equivalent of that. She's the astronomer Kevin Bacon. So there you go, complete. All the facts are in now.
All the facts are in.
All right, so I hope you all did your trivia, because now we're gonna go over answers.
All right. Okay. All right, so this month was acronyms. So, oh gosh, there we go.
I love that sound. All right, you want to start?
Sure. So question 1, which of the following is not an astronomy acronym? Alexis, Amanda, Amber, and Amelia. So Amelia is not an astronomy acronym.
OWL was a telescope planned by the European Space Agency, but eventually abandoned. What did OWL stand for? Was it overwhelmingly large telescope, owls who love telescopes, which I hope that's the answer, observatory wide and long, or ordinary wheeled telescope? Yep, overwhelmingly large. We're not the most creative. Granted, it's really straightforward. Like you can't go wrong with that kind of acronym. It's great.
It was huge. It
really was. If you see it, there's like a chart showing like different sizes of telescope mirrors, and the overwhelmingly large one it's just overwhelming.
It like
compared to the rest.
encompasses all of the telescopes that we have on Earth.
Yes.
Like crazy. Okay, question 3. Chaos is an adaptive optics system, but what does the CH stand for? Carbon, hydrogen, Chicago, chromium, or core hydrophobic? And the answer is Chicago.
I appreciate they used the first 2 letters and didn't pull randomly.
Yeah.
All right, what does COSMOS stand for? Cosmic Origins Massive Observational Survey, Cosmic Evolution Survey, Cosmic Origins Survey, Calculated Obstacles Situated Mostly in our solar system. It is the Cosmic Evolution Survey. It was mostly just representative, not actually an acronym.
Okay, this one was interesting. What are hot dogs in astronomy? Hot dynamical optical gears, hot doomed objects in gravity, hot dynamically observed galaxies, or hot dust obscured galaxies? Do you know what the answer is, Carving Queen?
You know, I do. I think it's the last one.
Yeah. I did not know this one because I'd never heard of dust obscured galaxies called hot dogs. So
yeah. They're also just dogs, and then they're hot dogs. There's a lot of food-related astronomy galaxies in there. All right, what does GRAPE stand for? Does it stand for Great Astronomy Personnel, which could always apply, Gravity Pipe, Graduate Professional Team, or Galaxy Reddening and Albedo Pipeline? It is Gravity Pipe.
One of the better ones.
Which I can appreciate, right? Like they took the first 3 letters and the last 2 letters. That's okay, I guess.
We get a little salty sometimes because acronyms don't always go great.
There are some train wrecks out there.
Yeah. What are machos? So A, moons and cold heavy orbiters, meteors and cold hot objects, massive compact halo objects, or magnitude amplitude central halo objects. And the answer is massive compact halo objects.
Okay then. Now, what are WIMPs? Are they weakly interacting massive particles, wildly inaccurate metallicity projects, which some astronomers might show with shade and say that's like most of XCal, weirdly inclined meteor peregrees, or wrongly ignored minor planets? Peregees, not peregrees. There you go, weakly interacting massive particles. That's a good acronym. It's the first letter.
Okay, what is the acronym that astronomers made from the following phrase? Balloon-borne radiometers, is it radiometers?
Yeah.
For sky polarization observation. I'm just gonna let you guys read it.
I really want it to be the first one.
Baboons, ballers, bar sport. Bar sports.
Okay. What does ELT stand for? If you remember our discussion about OWL, then you might be able to quickly guess. It is, if you can just click, it is the first one. It is an extremely large telescope. So we usually, there's like adjective large telescope or medium telescope or binary telescope. So that's a very common thing.
Creative one. Thank you for watching.
All right, and that is all the trivia. I hope you all were successful, although acronyms can be confusing.
Yeah. And we should go over announcements one last time.
Yeah.
Okay. So, whoops.
That sound.
Whoops. Okay. So, this is not the announcements we want. So, okay, as a reminder, like and subscribe to our YouTube channel. And the more subscribers we have, the more likely people will find us when they search in AoT. So please help us out with that.
Yeah. And feel free to follow us on all of our social medias. We have a Twitter page, AoT_BCS. We also have Facebook and Instagram with AoT BCS, no underscore. And then if you want to look at us on the official astronomyontap.org website, you can, but you can also look at all the other events that are happening all around the world from the other AoT groups.
And then help support our people at the Grand Stafford Theater. You can Venmo them Jose Quintana-20 or Jose-Quintana-20, and then you can put Stafford Tip in the description so that you're still supporting our bartenders that have supported us.
And you can also help support us if you feel so inclined. Feel free to donate online. We have a Venmo and Cash App, both are AoT BCS. And if you donate more than $15, you're eligible to get an AoT t-shirt, which sports the logo of this fancy lady here.
And our next Astronomy on Tap event is May 19th. And if you can't remember that, or if you don't want to put it on your calendar, just think about third Wednesday of every month. Third Wednesday.
Third Wednesday, number 3.
And that's it.
Yeah. So thank you so much for coming to Astronomy on Tap. We've had a great time, and we look forward to seeing you next time.
Thank you. Bye.
Out. Goodbye. So long. Farewell.
I think I stopped it.